Alright, hell yeah. So we got material mechanics, and we got that 2 hour problem, you know what I mean? That I think I can solve in 5 minutes, and that's what we're going to do. Because someone had kind of an, maybe thought I did it wrong. And honestly, doing the problem in 2 hours, the whole point for me was to get kind of close to the answer and not make a mistake. Because even running through the actual answer again, I made one critical error, so we're going to go over that. So we have this bungee cord, and then we're pulling with 80 newtons. And, the first thing that I actually did, I did this about 20 minutes ago. I have to write the material mechanics equations. That strength is force divided by area. That strength is modulus of elasticity times the strain. You know what I mean? And then strain is stretch, is change in length divided by length. And then I put these three equations together, basically into this one. Force over area is equal to modulus of elasticity, change in length over length. And then I can rearrange this multiple ways. But mainly I just want it rearranged for force is EA divided by L, change in length. Just so I have a check on reality that this force of a spring, you know what I mean? We have force of a spring is the spring constant times the change in length. Okay, hell yeah. So now we can start the problem. And this spring constant in material mechanic world is modulus of elasticity times the area divided by the length. Cool. So then the next step is kind of set up the problem. We're going to have 80 newtons up top, so we need an equilibrium. And we know once we apply, because the problem is set up where, hey, we have this length, the total length actually, L naught, of this whole thing is 0.76 meters. You know what I mean? So then one of these lengths is going to be L naught divided by 2. So hell yeah. So that's kind of what we have here. And then guess what? You know what I mean? That angle at the beginning is not going to be the angle once you stretch this hell up. That angle is going to get way smaller. So then we have to set up equilibrium that says when we put that AD on, at equilibrium, we're going to have some sort of tension in that cord, and that's the angle we're interested in. Okay? And that angle is determined by the cord is going to stretch. And then see this divide by 2? I actually messed up the problem. I'm just like, okay, this is just the total length of the cord divided by 2 plus the change in length. But no. You're going to have an equal change in length on both sides. Let's say that's your change in length. You're going to have a change in length there, and you're going to have a change in length there. And then these are going to equal your total. So it's best to say, hey, this is change in length divided by 2. This is change in length divided by 2. Because then, your total change in length of the cord is going to be on both sides. So this parameter right here is the total length of the cord divided by 2 plus the change in length divided by 2. Because that's really important. Okay, hell yeah. So now we set up the continuity, and we say that AD is only, the forces in the Y have to be balanced with the tensions, and it's only the vertical component of the tensions. We're going to have 2 of them, and it's the cosine component. It's not the sun is shining component, it's the cosine component of the tangent. Of the tension, excuse me. Cool, so there's an equation. And we can rearrange for tension, and then we got 40 divided by cosine theta. And then we know that the tension in the cord, from the material mechanics perspective of the cord is a spring, is that tension is going to be the spring constant, which is 140 Newton meters, times the change in length. Oh, sweet. You know what I mean? So don't we have... Well, we've only come up with these 2 equations so far. You know what I mean? So now what? Now what? Okay. Oh, yeah. I have no idea. I guess I figured out the angle. Is that the next thing? You know what I mean? Okay, for sure. Because we actually just have straight up geometry. You know what I mean? Never underestimate Pythagorean's theorem. It's just like, whoa, we know this length. Check that out. We have L naught divided by 2 plus change in length divided by 2. This height we don't know. Because we have the original height, sure, we'll know that in a second. But, you know, I mean, the original height was there, and now we've stretched the chord there. But what we're interested, if we're just interested in an angle, we only need to know two things about this triangle. So if this is the angle that we're trying to find, I'm going to say sine of this angle is opposite over hypotenuse. So that's what I did. B divided by 2 divided by L naught divided by 2 plus change in length. But again, I totally forgot that this should have been divided by 2, and so that's what we do. Okay, and then what I like to do is, sure, that's sine opposite over hypotenuse. But I like to do this, just cross out the sine and be like, well, I just want to find the angle. That's inverse sine. So that's kind of how I roll. So now in my calculator, no, I can't do anything yet. So now we have an equation for the angle. So this equation for the angle, the only thing we don't know is that change in length. Cool. So and this equation simplified to here. So we have this equation, let's say equation 1, equation 2, and then equation 3. We're going to throw this in for theta. Cool. And then we're going to throw this into t. So this is going to be k change in length. We definitely want to know that. And this is going to be 40 divided by cosine. It gets kind of heady. But then this angle, the whole angle inside is going to be inverse sine. This can simplify. Hey, we got to divide by 2 everywhere. So it's just going to be b divided by L naught plus change in length. And again, I messed up. I did. You know, I mean, my apologies, because I just thought it was change in length. I didn't realize, no, this is half. You know, the change in length on this side is going to be half of the total change in length. Cool. I think we spelled that out. Alright, so this is definitely not taking 5 minutes, but we'll probably get there close to 10. Alright, so then, this is where this problem sucks, because you want to throw this into your calculator as a solver. So I got it down to here, you know what I mean? And then the only variable we don't know is this change in length. So there's the change in length, there's the change in everything we know. This is 40 newtons. This is 140, it's the spring constant. This is this distance right here. And again, it should have been b divided by 2, but we factored out that 2. And this is length divided by 2, but again, we factored out all those 2's. And so we just have the original length, 0.76 meters, 0.38 meters. And now we're on a roll. And so what I do is, because these are equal, I'm just going to take this to one side and then just set it equal to 0. So that's kind of how I roll. I just don't want to write things 1,000 times. And now, so we throw this to our calculator. It's 40 divided by cosine, and then, you know, stuff gets real, and we got inverse sine, 0.38 divided by downstairs, 0.76 plus x. My variable in my calculator is x, and then so we have, and then minus 140x. You know, so we have this variable twice, and it's buried deep in here. So you need some sort of a solver, you know, use Excel or whatever. And then we graph that and find the 0. Whoa. And then find the 0, left bound, right bound. And on these graphing calculators, hell yeah, it'll save it right on the x. So now that we know x is equal to that change in length of 0.305 81172 meters. Okay, so now what can we do? Once we know that, we can solve all the equations. And what are we interested in? Well, I wanted to find that angle. That was the first thing. I was really interested. So we take that equation for the angle. It's just that 0.38 divided by 0.76 plus 2 times. Now this, did I mess up this? Hell yeah, I messed up this. Because, I forgot to chisel out all my air all the way through. That's why you see two different numbers here. Because, again, the whole setup was very important. And it's just so fascinating that you can mess up the setup. But if we do it with the normal numbers, I'll even do it. We'll kind of make this a longer video. So we got 0.38, just so you trust me. 0.38 divided by 0.76 plus that x value. And we get our angle, and I already stored that as alpha of theta, and we get 20.87, we get that, about 20.9 degrees. All these crossed outs are just like, hey, life is real. You know what I mean? My setup, I was a little bit wrong. I called this just change in length divided by 2, half the spring plus a change in length. But hell no, it's the change in length is on both sides. And so you got to divide that one by 2. Hell yeah. So then once we know that theta, I was just curious because I've done this problem before. I wanted to know the other angle. It's a right triangle, so if I know theta is 20, I go 90 minus that. And then I get 69.112. And that seems like a check on reality from when I did it before. Okay, what is this? What is this problem asking? You know what I mean? It says, well, first it says, what's the displacement of the original point? So this is where, hell yeah, you don't want to forget about Pythagorean's theorem. In the initial, heck yeah, I'm going to call this h, or h naught, the initial height. And then we have b divided by 2. And then we have L naught divided by 2, the total length divided by 2. So let's use Pythagorean's theorem. Here is the c side, so we're going to go L naught divided by 2. We're going to square it, and then we're going to subtract b divided by 2, this side, squared. Cool, and then the square root that. So that's what we got going on right there. And then we can find that initial height. And so now, what do we know? Well, we also know, so that's what I did. I found the initial height. So now we want to find the total height. And how did I do that? Like, what was my method? Well, I didn't want to do the Pythagorean theorem again. It is a good one to know, just to always have in your back pocket. But I was just like, well, I already found the angle, and I was really satisfied with that. That was 20.88. And so I just want to take this total length now, and we know that's that 0.76 divided by 2, or half the spring, plus x, our change in length, divided by 2. Sweet. So we know what that is, and we're going to take, and then we're going to multiply that by the cosine of our angle. And we're going to get, I feel like I totally wrenched that. What the hell? Oh, this is wigging me out. So 0.76 divided by 2 plus, and what's my x value? Yeah, that's right. It should be. And then, so that plus x divided by 2, that's going to be that total length. And then we have cosine, oh, wait, no, just, oh, I see. It didn't take that times cosine of the angle. You know what I mean? Holy Toledo. Hell yeah. And then we get that exact. And I wrote everything down exact to 10 digits. So if you do this on your own, you can check the 10-digit answers. So this is going to be my H final. And then they're saying, like, hey, what's the displacement C from, like, you know, initial to, like, up here? So that's going to be your displacement C. And it's just going to be that H minus the original H. I have these stored in my calculators, I minus H. And then we get 0.168794525. Answer in the back of the book's 1.68.1. I mean, so it's just, there's no error there at all. I can't imagine. But I'm just curious of different ways people do it. Just because you can do this problem 1,000 different ways, but you can make mistakes 1,000 different ways. So even when I set it up just to double check a person's, you know, approach, or just my approach, I made the mistake right off the bat of not setting it up right. Okay, so then the other question they wanted to know, so that was the displacement. They also wanted to know how much strain energy is stored in the cord. Now this is a fascinating one, because energy is force times distance. Well, isn't the tension in the cord T, and the change in length L? Hey, that's a good place to start, but just always asterisk this, because it is an integral, you know what I mean? That didn't have to fool you, but you start with zero force. There's no force in the cord, and then you put like a little bit of force in it, you know, and then it goes a little bit of a distance. And so this equation has to be force average times the distance. Well, we know what the max force is. That's what we just solved for that tension, you know what I mean? And so what we're trying to find, I mean, we just want to know the average force over that distance that we're pulling it. And the distance that we're pulling the cord is the change in length of the cord. You know what I mean? Like if we have a spring, hey, we're just changing its length from there. And in this, it's just the change in length. Can't say that enough. It has nothing to do with pulling it up. It's just, hey, the actual length got stretched. And so, and we have to use that average force, so we're going to take that max force divided by 2. But just even here, I was just like, well, what's tension? We already have that. It's going to be the spring constant times the change in length. That was from those original material mechanics equations. Okay, hell yeah, we're almost done. So then we have tension in the cord times change in length. You know what I mean? Or I guess this should be 1/2. I kind of threw it in down there. But yeah, so we have that max tension, half of it times the change in length. Sweet. And then we have an equation for the tension in the cord. The tension in the cord, or the max tension, is the spring constant times the change in length. So we have, again, energy is going to be the average force, which is going to be that max force divided by 2. So we're going to have K, change in length, 1/2 of that. That is our max force. I mean, this is it's our force average. Energy is the average force times the distance. So this is just the force. Now we have to actually multiply it by the distance, which is that change in length again. So it just happens that change in length was a function of, because of the spring equation, that change in length is a function of actual force in the spring. And then energy is that actual force times the distance. Now you got to do the 1/2 because we're talking about average force. Okay, so now we have 1/2 K change in length times change in length. And let me throw the half in there not to make. So yeah, we have 1/2 spring constant change in length times change in length. So hell yeah, we have 1/2 spring constant change in length squared. And so 0.5 times 140 times K squared. And we get 6.5, and then just to 10 digits. So you can actually double check this. Oh, it looks like my calculator wanted to do that in 8 now. Okay, and then we get 6.55 joules. And so that was the first answer for this problem. How much strain energy is stored in the cord. And then answer C, we'll just compare to the strain energy with the quantity of just displacing this distance. Hey, we had a force of 80 newtons, and we displaced it this distance. And again, we put 0 newtons on the cord starting, but then when we pulled on it, we pulled a max of 80. So again, energy is average force. That's going to be 40. It's the max force divided by 2. And we know the distance, delta C. So shouldn't that be our energy? And it's not. That's a higher energy, 6.75. And it's because, it's because of, we have a lower energy. It's because, I gotta stop because I want to say this right. Alright, hell yeah. So I apologize. I'm just going to have to call this a video. I even went to Excel to try to put this in, but I really do want to get these 2 graphs to kind of do the full explanation. I did it in Excel just a little bit. The fact that you pull down a little bit, hell yeah, you get extra tension. But, you know what I mean? I couldn't figure out, like, the percentages of that change in C. You know what I mean? It was a little bit too much for me to handle, so I apologize about that, you know what I mean? And I just don't want to spout stuff that's not true. So, yeah, we're going to be focused on that. I'm going to try to get a full Excel sheet going and learn how to... This sucks, though, because you have to solve this equation for every... Because I want 0 to 80 in my Excel, but I would have to solve this equation every time for the answer. And so that sucks. But anyway, I still want to post this video just because it was kind of a fast way to get to the answer and just to kind of, you know what I mean. So, hell yeah. Thanks for joining me, and that's the video.